Hello everyone, this is a video for Lab 6 in ENEL 270 on bipolar junction transistors. So for this lab we're going to be investigating the behavior of a particular bipolar junction transistor, the 2N3904 bipolar junction transistor, which looks like this here, standard 3-pin package for a through-hole transistor. Note that, like many components, this is polarized, that is, each lead corresponds to a particular connection on the BJT. That is shown in the lab sheet here. Make sure you know which way around your BJT goes so that you get your connections correct. The first thing we're going to do in this lab is check that our BJT is working correctly. A BJT is effectively a diode and a half sandwiched together. In particular, our base and emitter connection is just effectively a conventional diode as far as we're concerned for now. So what we can do is actually check that there is a forward voltage across our base emitter pair as we would with a diode to check that is working. To do that, we can take our multimeter, we can turn it to our diode tester, which is on the ones in the lab, the bottom here, with the picture of the diode and the little continuity tester icon in green. So we go around to that. We can then connect our multimeter across the base and emitter pins of the BJT. We want to forward bias, that is, put the positive connection from onto the base, and forward bias the base emitter junction, so put the negative lead on the emitter pin. Connecting those up for our BJT. Being careful not to short the leads together, otherwise you won't get an accurate measurement. If we connect those on, you should see we get about 0.7 volts. For these BJTs, and for most BJTs you will encounter, they are silicon based, and so you'll have about a 0.7 volt forward drop across your base emitter junction. If you do not get a 0.7 volt reading here, first of all make sure your connections are correct. Otherwise your transistor may be blown, you may need a new transistor, so just let someone know. Once you verify that your transistor is working, the next thing we're going to do is characterize our transistor's behavior. So we're going to generate a set of its characteristic curves. For our BJT, what we're thinking about here is the voltage across the collector-emitter junction. We're thinking about the amount of current flowing through the collector to the emitter, and we're thinking about the amount of current flowing into the base of our transistor. Note this is an NPN transistor, so current flows into the base to drive the transistor. For a PNP, current flows the other way, out from the base. Otherwise, they behave the same. To do this, we're going to use a couple of source meters that are in the lab. So go up to the front of the lab when there is time and go and talk to one of the TAs there, and they'll be able to run a test of that for you. What you will get are a set of what we call the characteristic curves for your BJT, which will look something like the example shown in the lab sheet. They will vary from transistor to transistor, but they should look similar to this. On the horizontal axis, there is the voltage here. This is the voltage across the collector-emitter junction, and we're sweeping this from 0 to 20 volts. On the vertical axis here, as labeled current, is the current flowing through the collector-emitter junction. So we think of this as being the collector current. We can see here this is stepped up in milliamps. And then you'll see a number of curves here. Note the bottom line here is just the horizontal axis. You can think of that as being 0 if you like. Each of these curves here then corresponds to a particular base current. For the setup we're using here, these are stepped in 10 microamp steps. So the first curve is 10 microamps of base current, the second one 20 microamps, etc. And so we can see that we get a different characteristic curve depending upon how much base current we supply to the BJT. So once you've got your curves for your BJT, append them into your lab report document. And there is a question here asking you to explain how the Keithley source meters, these are the devices we're using, generate the curves that you get for this BJT. How do they generate those characteristic curves? So have a think about how, if you were testing these, you might generate these curves. Have a chat to the TAs if you're not sure as well. And if you like, observe the source meters running and see if you can see what they're doing. Once you've done that, you can identify 3 particular regions on your curve: the active or linear region, the saturation region, and the cutoff region on your graph. And you can refer to the notes from class if you're not sure what those regions are. We can then, using our graph, determine what our DC current gain is, our beta value, at DC for our transistor. In this case, we've asked you to do it at 20 and 40 microamps of base current, and using a collector emitter voltage of 10 volts as well for your calculations. So what you can do is, using your particular characteristic curves, find the curve that corresponds to 20 microamps of base current, and at 10 volts VCE. You can then trace up where that is on here and measure across to find the amount of collector current. From that, you know the collector current, you know the base current. You can calculate the beta DC value. Repeat that as well for your 40 microamp base current to check that your results are reasonably consistent. And you should find they're about the same. You're then asked to check that these results for your beta values correspond to the values from the manufacturer's datasheet for this transistor. On the very back of this lab document, you'll find an excerpt from the datasheet here, showing you a few values, one of which is our beta DC value, our DC current gain. Note on the datasheet here, this is not labeled beta, this is labeled HFE. This is from a different way of parameterizing the behavior of a BJT. The value is the same thing though. So you're looking for the DC current gain value here. You'll see there are a number of different test conditions there. Find the one that you think is most appropriate for the kind of setup we're doing here. And check that your beta values, the ones that you calculated, fall within the range specified by the datasheet. If they don't, I suggest you double check your calculations, make sure things have been done correctly. You're then asked to determine, or estimate at least, the AC current gain, where instead of looking at fixed values of current and voltage, we're looking at small changes in current and voltage, and see what our beta or our gain value is there. You will find that because we only have a finite set of curves for each different base current value here, you probably need to interpolate, that is, estimate between these curves what the base current is. So knowing, stepping between, say, 10 and 20 microamps, if you're somewhere between those, you know that's somewhere between 10 and 20 microamps, and you can linearly estimate or interpolate to figure out what that base current should be. So you can then estimate the beta AC value, and there's a short question here just asking you about what the significance of this value is compared to your DC value. So have a think about, in an AC application, why that might matter as opposed to in a DC application. Okay, the next thing we're going to do is look at a linear amplifier application using our BJT. What we're going to end up building is the circuit shown in the lab document here. Now we're using a voltage divider bias here for the base biasing for the BJT. We have our DC biasing section in here, and then a few capacitors for coupling in and out for our AC section. The first thing we're going to look at though is our DC biasing. So I've constructed just the DC portion of the circuit here. That is, I haven't connected any of the capacitors in, nor have I connected in any oscilloscope probes, nor the sinusoidal waveform shown that we're going to connect in later. You can connect those in now if you'd like to, but I find they tend to get in the way and add a bit of clutter. So for just doing the DC biasing analysis, I find it's easier to keep the circuit a bit cleaner and just put in the components we need. To be a bit explicit, for our DC biasing, all that we need are the collector resistor, the emitter resistor, and the two base resistors for this voltage divider bias. Okay, so I've set those up. What we are going to do for this section is, first of all, do a load line and operating point analysis. So what we can do is, using our circuit diagram, now we've got 15 volts coming in to our base voltage divider, we can determine what our base current should be, assuming that we have our base emitter voltage of about 0.7 volts. Again, if you're not sure how to do this, remember we have a voltage divider here. We need to quickly do a Thevenin equivalent circuit, and that will be covered in your notes from the lectures. So you can calculate your base current. We can then draw on our load line, characteristics graph we generated before. We'll draw a load line on that, corresponding to VCC as 15 volts, and our collector and emitter resistance of being 2.5 kilo ohms. When we're drawing our load line on our plot, so on our characteristic curves, looking at the common typical ones here, what we're doing is we're thinking, okay, what is our circuit going to do when it is in an open circuit, that is, no current is flowing? And what is it going to do in a short circuit when there is basically no voltage across our circuit? This gives us two extremes. Knowing that our circuit is a linear circuit, we can then draw a line between them. So thinking about having 15 volts here, if we consider what happens when our circuit is open circuit, that is our transistor is off, there's no conduction, assuming there's no leakage, we can say, well, at 15 volts, we know there's going to be zero current flowing into the base. And so zero current flowing through the collector. That gives us 1 point on our graph. Similarly, we can say, well, if there's a short circuit, there is some amount of base current flowing. We know there'll be no voltage across the collector emitter junction because it's in a short circuit. And we know the maximum amount of current that can flow is then limited by the collector and emitter resistance. We know we've got a 1.5 kilo ohm resistor from our collector and a 1 kilo ohm resistor from our emitter. So that total series resistance is 2.5 kilo ohms. So now we've got 15 volts being supplied and 2.5 kilo ohms of resistance. We can determine how much current will flow if there is no voltage across the transistor. That will give us a point up here on our vertical axis. We can then draw a line between those 2 points, and that is our load line. Then using your load line and knowing how much base current will be flowing in this circuit, we can determine the intersection of those and find our operating collector current and collector emitter voltage. Note that the base current you calculate is unlikely to be one of those 10 microamp increment curves. So again, you'll need to estimate where that curve would be on that graph. From that operating point, you can then estimate, as I said, the collector current that should flow in this circuit and the voltage across the collector and emitter of this circuit. Once you've done that, you can then use the actual physical circuit to measure and validate those results. The three things we're going to measure here are the base current, the collector current, and the collector emitter voltage. I'm actually going to run through these in reverse order so I can talk about them as I go. First thing I'm going to do is measure the voltage across the collector emitter junction. That's quite easy for us to do. So with our power supply set up at 15 volts, turn that on. Set up our multimeter to measure the voltage across the collector emitter junction and connect in across the collector and emitter. And you'll see some voltage being read out there. What voltage you get and what voltage you expect will vary from transistor to transistor, so this result is not globally applicable. What you get will depend upon what you're working with specifically. However, you should see some voltage across the collector emitter. For example, here I'm seeing 5.78 volts across my collector emitter junction. I can compare that to what I estimated from the load line analysis and see if that corresponds or not. We can then measure the collector current. The way I like to do this is quickly pop power supply off. I'm going to turn the multimeter off so it doesn't beep at me as I change connections and disconnect it from the circuit. I'm going to change my multimeter over so I'm measuring current. I'm going to turn this into current measuring mode as well. And what I'm going to do is I'm going to move the collector resistor. Currently I've got that directly connected to the collector of the BJT. I'm going to move that off somewhere else on the breadboard, just a little bit away, and then insert the multimeter acting as an ammeter in between the two. So the positive lead to the now open end of the resistor, and the negative lead to the collector of the BJT. That way current will flow from the supply through the collector resistor, through the multimeter, through to the collector of the transistor and the rest of the circuit. And we can intercept that and measure that in between. The notes mentioned you can also determine that by measuring the voltage drop across the resistor. We could also measure the voltage across the collector resistor and use Ohm's law to calculate the collector current. They should both give the same result. I'm just showing you this way of measuring current as it takes a bit more setup work. So if I turn the power supply on and change the ammeter to be in range, I will measure some current flowing into the collector. Again, for this specific BJT, I'm measuring 3.7 milliamps flowing into the collector. What value you get and what value you should expect will vary depending upon which transistor you're using. So this is not generally applicable to all transistors. Okay, so that is the collector current. I can then turn off the supply, reconnect the collector resistor back to the collector. The last thing we want to measure is the base current. And again, we have two ways of doing this. We can measure the voltage drop across our known resistances and thus calculate the current from that, or we can measure it directly with the ammeter. Note that this is a little bit more difficult because we have a voltage divider bias here. If we just measure the voltages across these resistors and calculate those currents, we'll find we'll get something probably in the hundreds of milliamps, whereas we're expecting something in the microamps for the base current. What we would have to do to measure the base current via these voltages across these resistors is measure the voltage and thus current flowing through both resistors and work out the difference between them. The idea being that if we're thinking about our voltage divider bias, some amount of current will flow from our supply through this top resistor, and then they'll branch. A little bit of current will flow into the base of the transistor, and the rest will flow through this bottom resistor here. If we work out the difference between the current flowing through this top resistor and the current flowing through this bottom resistor, we then know how much current is flowing into the base of the transistor. We can do that directly by measuring those voltages. However, you may find it's hard to get the required resolution by measuring those voltages. You'll find that the voltage and thus currents are relatively high compared to the amount going into the actual base of the transistor, and so you will get pretty poor resolution with that. The other way of doing it is again to directly measure the current using our ammeter. So I'm going to show you how I would do that. What I would do is take these two resistors here that make up this voltage divider bias and actually move them over a little bit. So I'm going to move them over here. Same kind of connection to the top one from the 15-volt supply into the breadboard, and the bottom one from the same node on the breadboard to ground. So at the moment, current's going to flow through this top resistor and then back to the bottom resistor to ground. Again, I can then insert the ammeter, one connection at that node and the other at the base of the BJT. That way, current flowing into the BJT will have to flow through the multimeter first. If I do that, turn the power supply on, I'll need to dial the range on the multimeter to get an accurate reading. If I dial that to the microamp range, for this particular BJT, I'm reading about 22.6 microamps of base current. Again, that will vary depending upon your transistor and its particular operating point. Okay, those are our DC biasing values. So you should have some from your load line analysis and now some from measurements. You should compare those together and see if they correspond or not. As a note here, and this is in the lab document, if your collector current values don't agree to within about 20%, check that your circuit analysis are correct. If they're that significantly off, so by more than 20%, there may be some kind of issue, which may make your later AC analysis a bit difficult to do. The next thing we're going to do is move on to our AC analysis. So at this point, if you haven't already, you'll want to connect in those three capacitors, plus the wave gen. I'm using the wave generator from the oscilloscope, and a couple of oscilloscope probes. One to measure the signal coming from your wave generator, and one to measure the output voltage of your circuit. Note that on the circuit diagram, our input from our wave generator is going through that 10 microfarad capacitor. If you're going to measure that waveform with an oscilloscope probe, measure before you go into the circuit itself, so before you go through the capacitor. And for the output signal, we're measuring on the other side of this capacitor that's connected to the collector. And that's represented by this R scope, this 10 mega ohm resistor here. This is not a resistor you need to add to the circuit. This is representing the oscilloscope probe. So just bear that in mind. Okay, I have set up the wave generator here to generate the desired waveform. We want, in this case, a small waveform of about 20 millivolts peak to peak. That's what I've set on the wave generator here at 10 kilohertz. And you can see that on the yellow channel here. So that's our input waveform. I'm also measuring the output waveform. If I turn the power supply on, you'll see that'll start to settle in a minute as we measure the output voltage of the circuit, which is in green. You can see that's coming down the screen here. That's due to this capacitor here needing to charge up. If that's taking a while, or if you find you're turning this on and off a lot and having to wait, what you can do is change the what's called the coupling of this probe. So if I go to the channel 2 options, by default it's on what's known as DC coupling. I can change that to AC coupling, and that will then get rid of any DC component of what I'm measuring. Make sure if you do this, make sure you remember that you have If you're measuring stuff that has DC in it, you won't be able to see it here. And I'll come back to that again in a minute. So, with both the input and output waveforms being measured, you can measure their peak-to-peak voltages. You can then determine what the no-load voltage gain is, which is the first question for our AC analysis. You can also use equation 6.1, back at the top of the amplifier section. Knowing the collector current that we just measured in our DC biasing, and we know the rest of the values here, we can calculate what we expect the voltage gain to be. So we can calculate it, we can measure it, and then we can compare the two. That's what the next part is asking about, is to calculate what the expected gain is and discuss the differences, if any, between the two. We've also asked you to reproduce the waveforms shown here. You've got a couple of options to do that. One is that you can, if you wish to sketch on the graph paper here, that's absolutely acceptable. The other option is that you can use what's called the bench view program on the lab PCs. You can use that to connect the oscilloscope and basically capture the image on the screen here. There are a couple of things you've just got to be aware of when you do that. So if you wish to do that and you're not sure how to, feel free to ask one of the TAs. Either way, you need to reproduce these waveforms here in your report, and make sure you do so unambiguously. That is, make sure they are appropriately labeled so that when we're looking at these, we can see what it is you are graphing. The next thing we're asked to do here is to use the oscilloscope and the oscilloscope probes to view the voltages on either side of capacitors C1 and C2. So these are these capacitors here, one going from our input signal through to our circuit, and the other one coming from our circuit out to our output voltage area where we would load this up. So we can use our oscilloscope probes to do that. We can put one probe on one side and then move it to the other side and see what the difference is. Note that if you've changed the coupling of either of these probes to be AC coupled, you'll want to put it back to being DC coupled. Otherwise, you won't be able to observe the intended behavior. So make sure you do that first. Okay, so have a look at what happens either side of those capacitors, and therefore think about what these capacitors are here for. What is their purpose in this circuit? Once you've done that, we then ask you to remove capacitor CE. That is the capacitor at the emitter here. You can see that is in parallel with our emitter resistance. So we can remove that capacitor, and you can do it just by going in and pulling it out of the circuit. I'm just going to disconnect it here. And we can then look at what happened to the output voltage. You will probably need to rescale that on the oscilloscope. Rather than auto scale it, we can just use the voltage scale dial on that channel to rescale it and see what's going on. So I've asked you to remove that capacitor and then re-measure the gain of the amplifier. Same way you did it before, compared the output voltage to the input voltage. Having calculated that new gain and thinking about what it was and what it is now, think about and discuss briefly why this capacitor CE is in the circuit and what it does. Okay. Once you've done that, you can reconnect in the emitter capacitor. Note that when you're putting the capacitors into the circuit, you'll want to be a little bit careful that they're making good connections because they have asymmetric length legs, so they can be a bit fiddly to get in properly into the circuit. So just be careful with those. The last thing you're going to do in this lab is take a 1 kilo ohm resistor and use it to measure the input and output impedance of the circuit. The same way we did back in lab 1 where we had that non-inverting voltage amplifier. So if you're not sure of how to do that, refer back to your lab 1 notes. What we're going to do is take this resistor and first of all connect it in as a source resistance. The easiest way to do that is to disconnect the wave gen and the corresponding probe from the circuit, and then connect that resistor coming out from that input capacitor to somewhere in the breadboard. It doesn't really matter where. We can then reconnect in our oscilloscope probe and the wave gen signal, make sure our circuit is still working properly, and then go through our procedure to measure the input impedance of this amplifier. Being careful of which voltage you're measuring on either side of this resistor and how you label them. Remember, effectively what we're doing is we're thinking about this as forming a voltage divider. We can think about the currents flowing into the circuit as well. If you're not sure how to do this, create a simple sketch of the circuit, just representing the input waveform as some voltage source, think about the source resistance you've added, think about the existing resistance, the input impedance of the circuit, and you can just connect that to ground for simplicity's sake. Okay. Once you've measured the input impedance of the circuit, we can then do a similar procedure to measure the output impedance of the circuit. So you can disconnect that input source impedance, that added resistor, and move the input waveform and oscilloscope probe back to where they were originally. And then we can take this load resistor and we want to connect this from our output voltage of our circuit to ground. On our circuit, our output voltage is coming from the output side of this capacitor here that's connected to the collector. So this side, we've got this oscilloscope probe, that's our output side, that's our load side. So what we can do is connect a resistor from that side to ground. That gives us some sort of load resistance. With that, we can then, again, using the same procedure as in lab 1, measure and figure out what the output resistance of this circuit is. Now, of course, we're doing this at 10 kilohertz. If we change the input frequency, we may well get a different impedance, depending on the frequency dependence of the circuit. That is the last part of the lab. What we then ask you to do is, as usual, summarize your results in this little table here, and then comment on, based upon what you've measured here, what you think about the suitability of what we're calling current-controlled BJTs for linear applications. In other words, think about whether you think this circuit is suitable for a linear amplifier application like we've done in this lab. Think about what makes it good for that and what potential problems or shortcomings there are of this circuit. That is the end of lab 6.